Today, Clark Barwick will be speaking about exodromy and endodromy, but before he begins, anyone who is presenting a poster during the poster session tomorrow should speak with Dan Isaacson, who's over here, before you trot off after the talk. So I'll try to remind you again at the end, but be prepared to do that. So without further ado, Clark.
Thank you. Thank you to the organizers for allowing me to come here and speak, and to the organizers of the semester overall. It's been really, really fantastic. This talk is a little bit out of line with the general nature of the workshop, I'm afraid. So I want you to take that as an invitation to ask me lots and lots of questions. In particular, I've sketched here a sort of plan for the talk, but I mean, this is ridiculous. I probably can't say all of this. I'm not devoted to saying any one thing. So as long as I've spoken about the closure in the Alexandrov topology, then I can talk about the next thing. So you know.
The word endodromy doesn't occur over there.
It doesn't. It's implicit in this bracket here in the word Verdier duality, and I hope I'll be able to say that. So I have to start somewhere. So I want to talk first about Galois invariance. And well, so the first thing to explain is that in algebraic geometry, the way one constructs a fundamental group is not the way one constructs it in topology. One has to build not paths into your space, but one has to use covering space theory in order to construct the étale fundamental group. So the basic idea of, say, the étale fundamental group, and I'm going to put a little hat here for reasons that I'll explain in a second, is that, well, if you've got a reasonable scheme, and I look at the category of finite étale coverings of that scheme, then that scheme is actually, then this is actually naturally the category of functors from something, which I'm just going to denote like this, from X, in this case, to finite sets. That something is a groupoid, but it isn't just a groupoid, because we can only speak about finite étale covers. Well, that's not true. We can talk about profinite étale covers, but one has to be very careful about this. And so this thing is a profinite groupoid, right? So it's a pro object in the category of finite groupoids. And well, if your X happens to be connected, and connected turns out to just mean the same thing as Zariski connected, then this is B of a group, which is the étale fundamental group. And it's a profinite group. It's not just a group, it's a profinite group. So you can think of that as a topology or what have you. So let me give you a couple of examples of computing this thing. Well, one you already know, I'm sure, very well, which is that if I take spec k for your favorite field k, then this is nothing more than, well, let's see, let me take the capital guy, since I'm going to be talking about capitals all the time. This is nothing more than B of the absolute Galois group of k. So the Galois group of the separable closure of k over k. Okay. And I'll keep my hats on here to remind me that everything is profinite. And for those of you who are experts in these things, I'll only be speaking about profinite things. There is just a strict pro-group story that I could tell you about, but I don't want to. So let me give you another example. Let's say that I've got a curve over a field. So let's say that C is smooth over K, and let's say that its Euler characteristic is less than or equal to 1. Then this is also B of a pi 1. Well, this is a stupid thing to say at the moment, but it will become more interesting in a moment when I change this. The nice smooth connected curve. So we don't know much about these fundamental groups. Let me give you an example to prove that. Well, let's just take the simplest thing I can think of. Let's take the affine line. K is now, let's have K even be algebraically closed, so I don't have to worry about anything coming from the absolute Galois group of K. And I'll just try and write this down. So if you're topologically minded, as you might be if you're in this room, then you might expect the affine line to be simply connected, and you'd be absolutely right, provided the characteristic is 0. If the characteristic is not 0, that's not true anymore because of the existence of things like Art and Schreier covers. And in fact, no one knows the answer. Now, I say no one knows the answer, but we actually know a lot more about this group than we did 30 years ago. I mean, this is an incredibly simple situation. There's no arithmetic coming from the field, and there's no funny business with the geometry. It's just really, really, really not simply connected. In fact, this isn't even a topologically finitely generated group. So there is something really non-trivial that we can say about this, which is Abjankar's conjecture, which is now proved. So this is also known as Raynaud's theorem. And what does it say? Well, it says that it tells you what groups can appear as the finite quotients of this group. So if I look at the set of finite quotients, of this guy, then this is the set of, or the class of quasi-P groups. Well, it's a set. Quasi-P groups are the groups that are generated by their PC-low subgroups. And these are exactly the things that can arise here. So for example, in characteristic 2, one thing that tells you is that every symmetric group appears as the Galois group for some covering space, right? I'm telling you that a group is a quasi-P group if and only if it's the group of deck transformations for some finite étale cover of A1 over, say, any field of characteristic P that's algebraically closed. This is this class.
P is the characteristic of K.
This P is the characteristic of K. Yeah, maybe I should have said that. Yeah, that P is that P. Okay. So this is quite a striking theorem. How does one prove this theorem? It's actually, as you might expect, quite difficult. It's relatively easy using ordinary Galois theory to show that anything that is a finite quotient of this must be a quasi-P group. That's something that isn't too hard to check. It's the other direction that's complicated. This idea that taking a quasi-P group and actually constructing out of it some cover. So how this is done is by what's called rigid patching. And so the idea is that you have to pass to some sort of analytic type varieties and do some patching there where you can get control over things, and then use some techniques of algebrization to tell you that you can go back to the original algebraic zone, some algebrization techniques. And that's the kind of strategy that you use here. And indeed, anything that's sort of this form, anything that's the story of, you know, some variety of characteristic P over an algebraically closed field where you're trying to write down the finite quotients of this, all the examples I know are built using that kind of strategy. There are various forms in which it takes, formal things, rigid things, what have you, but they all look the same way. So this is the Abjankar conjecture. So this is just to argue that these invariants, even when you pass to what sort of seems like a fully geometric situation, are subtle invariants. Let me give you an elaboration of this and tell you a result. So this is just pi 1. What do the higher pi i's look like? That's only natural. And so this pi 1 here was defined by sort of representing a functor in a weird way. You would never teach someone about fundamental groups by saying that, but this is what we're doing. So you can try and do the same thing if you're willing to work with infinity categories of things. That is to say, we're going to look at X, and we're going to look on the étale side of X, and then we're going to look at the local systems, the least sheaves. So what are these? These are locally constant étale sheaves on X with the property that the stalk at any point is a pi finite space. So pi finite just means that you have finitely much homotopy and all of it's finite. Pi naught's finite, pi 1's finite, and so forth, and it stops at some point and you just get zeros after that. So that's what this category is. It's the category of étale sheaves that are locally constant and pi finite in the sense that I just described. And now what you do is you try to fill in the blank. So I'm trying to just go to pi finite spaces. And the good news is that you absolutely can. You can't fill it in with a pi finite space. That would be too much to ask for. But instead, you fill it in with a pi profinite space. A pro object in pi finite spaces. And from now on, I'll just say profinite space when I'm talking about a pro object in pi finite spaces. And this is a perfectly good definition of this object. I beg your pardon? This is the category of pi finite spaces.
Oh.
S just means space, pi means pi. Or pi finite or something. And this is a complete description of this thing. It might not be the most comfortable description you've ever seen, but it is a complete description of this thing. And now, I wrote down this rather stupid formula here, and you might have been offended by it, and you'd be right to be so, because, well, it isn't much of a sentence, right? I mean, I'm just saying that C is connected. But now I get to say something much stronger, which is that, in fact, this is true. Curves with this, as long as you're not P1, basically, curves are K pi 1s. They're just this. That's not true for surfaces. It's wildly untrue in the same way that we have in homotopy theory. But this pi infinity is also this pi infinity, so.
Is the pi infinity the thing people sometimes call the étale realization?
Thank you. It is. It's the, well, there are various names for this. The way I've written this is that this is what's normally called the étale homotopy type. Let me emphasize that when I'm talking about this, I'm talking about least sheaves of spaces. When we talk about sheaves of spaces, we don't just talk about, a short exact sequence. We have to use the entire resolution when you have a system of open covers. So this is a sheaf in the infinity categorical sense. So this is a nice invariant. Let me give you a theorem about this invariant, lest you wonder what this has to do with anything you might be familiar with. This is a theorem of Artin and Mazur.
Didn't you just change only the left-hand side of those equations?
Wait, I have to remember my left from my right. Yeah, I just changed the left-hand side of those two equations. That's right. And I'm saying there's just nothing happening in higher homotopies for these things. Fields are dimension 0. There just isn't anything happening in higher homotopy. Curves, at least as long as you're not P1, are also dimension 1, and therefore they don't have any higher homotopy. But as soon as I introduce a surface, it'll have lots and lots of homotopy. It's the same kind of phenomenon that we see in homotopy theory. Okay, so let me tell you what the statement of Artin Mazur is. Well, suppose that I've got something of finite type over the complex numbers. Well, then what can I do? Well, there are two things that I could associate to this that could be naturally called the homotopy type. One of which I've just told you about. I've just told you about taking pi infinity of x as an étale thing. So maybe I'll scribble an ET to remind us that this is the étale thing. Another thing I could do is, well, this is x over a finite type. So if I look at the complex points of this thing, then that's a topological space. It's a complex manifold with corners or something. So I've got myself a nice complex manifold. I can look at the analytic topology on that, and I can look at the homotopy type of that thing. So I can look at the underlying homotopy type, that's all this pi infinity means, of the complex points of x with the analytic topology. And these two aren't the same usually, but they're the same up to a profinite completion. This thing might not have been profinite when I started, so I have to fix it. So this is the theorem of Artin Mazur. maybe I'll just take a moment to say that the Art and Mazur theorem also works in more generality. So this also works over, well, let me just say analytic fields, or yeah, I'll just write analytic fields, and I can give you a more precise statement later with Berkovich spaces. So if you want a version of this over CP or something like that, you can also have access to it. Okay, so that's the story of these invariants. Now, what we're getting here is we're getting local systems, right? And this is an example of what's called the monodromy equivalence between two things. This is a familiar concept, which is that, you know, if I have a locally constant sheaf of vector spaces, and I've got a loop in my space, then I can take a vector and I can track it around with the loop, and that'll give me a representation of the fundamental group on that fiber. This is a familiar concept. And this is just a very abstract version of the same sentence. I don't know if it's that abstract, but anyway, it's there. So now the question is, can we get a finer invariant of this thing? That is, well, when I think about the Abyankar conjecture, I'm thinking about coverings of A1, but another way to think about coverings of A1 is to think about branched coverings of P1, where the branching all stays at infinity. That's a special characteristic P phenomenon, but it's one that I want to study. I want to study coverings of P1 where I control somehow what's going on at infinity. And I try and keep track of that information in some real way. Now, P1 doesn't have any étale covers, regardless of the characteristic. As long as I'm algebraically closed, P1 doesn't have any covers. So I want to be able to give you an invariant that somehow knows what's going on at infinity in a systematic way. So how can I translate that into this sheaf theory language? Here I'm talking about locally constant sheaves of pi finite spaces. So I want to be able to get the same idea where I can have something strange happen on some subvarieties. So that leads me to the notion of a constructible sheaf. Is this legible?
Yes.
This is this nice Hagoromo chalk, so I'm going to keep using it till I run out. Or until someone really nice who happens to have some gives me some. No? Okay. No one wants to give it up. Let's see. Right, so what is a constructible sheaf? A sheaf F for the étale site is said to be constructible. Well, I'm going to say something stupid right now. I'm going to say it's constructible if it's P constructible for some finite constructible stratification X zar to P. Well, that's not a helpful definition because I haven't told you what P constructible means yet, so I better do that. And I also haven't told you what a finite constructible stratification is yet, so let's do that as well. So P here is just going to be finite, just means that P is a finite poset. So that's all that word means. A stratification is just a continuous map. This is the Zariski topology, and P here I'm endowing with the Alexandrov topology. Right? So in the Alexandrov topology, the sieves are closed. So that's what this topology is. And I'm just asking for a continuous map there, and that's enough for me. To say that it's constructible, however, constructible means, well, what can I do? I can look at X zar, I can map it down to P, and I could do something like look at an open that looks like this.
Dr. Clark,
Yes, sir.
this is the lecture on the Alexandrov topology when I was in high school. So,
Yeah, so
Just
I mean, specialization goes to less than or equal to, and what does it mean in terms of just...
Yeah, let me just say. So U and P is open if and only if, well, if I have x less than or equal to y, and x is in U, then y is in U. So it's the upwardly closed guys. That's the Alexandrov topology. And so in particular, if I choose a point P inside P and I look at the set of things that are bigger than or equal to P, that's certainly a big open. It's a quasi-compact open because P is finite. And what am I going to require? I'm just going to require that xr greater than or equal to P, which is open, also be quasi-compact. So constructible means that this guy, for any P, is quasi-compact. Another way of saying the same thing is that the map is just a quasi-compact morphism. Quasi-compact continuous map. The inverse image of quasi-compact opens are quasi-compact. Okay, so I'm nearly there. I've told you everything except for the meaning of P constructible. Now I have to tell you what the word P constructible means. And what do I mean by P constructible? I just mean that on the strata are the inverse images of those points. Those points are locally closed subsets of xr. On those locally closed strata, so P constructible means for any P in P, if I look at my sheaf F and I restrict it to xp, this is this inverse image of P under this map. That's a locally closed guy. And what is this? Well, I'm looking at it with the étale topology again. I can ask it to be least. And that's what I mean by P constructible. The reason that you might, yes?
X sub P is the stratum?
X sub P is the stratum, that's right. So if I take a point P inside here, I can get X sub P, and this is locally closed. In general, neither open nor closed. It's just some intersection of a closed and an open. And I'm going to restrict F to that, look at on the étale topology of that, and require that it be least. Right? That is to say, locally constant with pi finite stalks. So this is an elaboration of this least category, right? We have a bigger category here, which is this constructible category. The reason you might want to contend with this is, well, if you're thinking about, for example, a situation in which you've got a nice local system on some moduli space, and let's say you compactify that moduli space and you push forward that local system, well, it's unlikely to be a local system anymore. Even if you do it in a derived way, even if you get all fancy homotopically, it still won't be a local system in any real sense. So you really have to pass to this bigger category of P constructible things, or of constructible things. Okay, so then now what I'd like to do here is I'd like to give an elaboration of this equivalence up here between least étale sheaves and functors from this pro category, or pro groupoid, and I'd like to give an elaboration of it that works for constructible sheaves. Right, I'd like to replace the left-hand side with constructible sheaves and replace, well, pi infinity et with something. So this is what I want. Equivalent to functors from something, which I'm just going to give a name to without really. I have not identified this yet, right? This is a blank. This is the thing that I want. Pi finite spaces. I want to represent that functor, if you like. And the value of this is that this means that I'm going to be able to hopefully keep track not only of the sort of monodromy of a local system over A1, but also what happens out at infinity when the branches come together. That's exactly my task. All right. So my motivation is here, comes from Galois invariance. And so now I want to tell you the story. I want to tell you what the answer is to this story over here on the topology side. This is a known story on the topology side of things. And then I want to go back and tell you how to adapt that story to the context of algebraic geometry. Everybody happy? Is anybody happy? Okay, good. All right, so here we go. So, wait, was someone not happy? Who was unhappy? I'm not in on the joke. That's okay. All right, so what can happen? So if I talk about a topological space, and I talk about a stratification of the topological space, well, it means exactly what it means here. It means a continuous map to P where I equip P with the Alexandrov topology. So I can talk about constructible sheaves on that, right? So this all makes sense for any topological space, where here I don't take the étale topology, I'll just take the topology of that topological space. I won't try and be fancy about it, I'll just try and work with the topology of that topological space. So for example, well, x to p continuous, this is what I mean by a stratified topological space. What can I do? Well, what I can do now is I can try to understand the usual definition of the singular simplicial set of x, which is sort of a model, an algebraic model for the homotopy theory of x, but relative to this stratification. So I'm going to form, so I don't know, here's a definition. I'm going to form a new simplicial set, which I'm going to call pi infinity 1 of x relative to this stratification. And here's how I'm going to do it. Well, first I'm going to look at the singular simplicial set of x itself. Right, pi infinity x means the singular simplicial set of x itself as a simplicial set. I mean this set theoretically right now. So the n simplices of this are the topological n simplices of my original x. And now that maps down to pi infinity of p. Now, there's a canonical map from, now this is a simplicial set, so I can think of p is a post set, I can think of that as a simplicial set by taking the nerve or something. I'll just call that p again out of laziness. And there's a canonical map going like this. What is that map? Well, if you think of P as a simplex, then the stratification sort of looks like this. This is a delta 2, and I'm telling you what the stratification is of its topological realization. Right, so I've got one closed point here. I've got this locally closed bit here. And then I've got this further open bit up here. And this is a stratification of delta 2, or the realization of delta 2. And that stratification of the realization of delta 2 corresponds to a map that goes like this. And what am I going to do? I'm going to form the fiber product. The literal fiber product. Not homotopy, not fancy, the literal fiber product. What is this? This is an exit path object. The zero simplices of this are just the points of your original x. Nothing else happened. Nothing happened at the level of zero simplices. But the paths, the one simplices, the paths have to go out. So this is a low stratum, this is the zeroth stratum, this is the first stratum, this is the second stratum. Your paths have to exit. They have to go out like this. They can go this way and then go out. And once they've gone out, they have to stay out.
Mark,
yes?
what does this picture have to do with P mapping to sing P?
So this is a stratification of...
Where's the P?
P is brackets 2. It's the 0, 1, 2, that post set. And all such P's are obtained by taking colons of such things. So this tells you what goes on in general. And so this is a stratification like that, and that corresponds to a simplicial map from delta 2 into pi infinity of brackets too, regarded as a topological space. And so these paths have to go out, right? So they have to go from a low stratum out to a high stratum. And once they go out, they can't go back. So you're allowed to stay in the stratum you're in. That would be a valid option for you. Or you can go out and then hang out there, but you ain't coming back. And those are the rules. So it's like a high school lockout or something. Have I already made that joke? Anyway, so there it is. So this is just a rigid simplicial set that I just sort of wrote down by fiat. I haven't told you that this thing has any sort of homotopical content yet. And as a topological space, or as a weak homotopy type, in good cases, it's actually just going to be equivalent to this again. There's not going to be a difference here. Provided X is a sort of nice enough topological space, as a weak homotopy type, you're not going to see a difference here. But the point is, you don't want to look at this as a weak homotopy type. You want more refined information. So let me tell you the theorem. So the theorem is that this is a quasi-category. Well, that's one of the theorems. So here's the theorem. So this is originally an idea of Bob McPherson, and then his student David Truman refined it, and then Lurie refined it more. So the first thing to say is that this object, which I've already suggestively named pi infinity 1 xp, is a quasi-category, or in my parlance, is an infinity category. Second, well, if we think of this map here, this vertical map that I've got right here, well, what can happen? So look at a fiber over a point down here, right? That point consists of exit paths that stay exactly in your stratum. Well, they're allowed to be reversed, right? If you're staying in one stratum, you're allowed to go out and back and do whatever you like. That's actually just the fiber over this is actually just the homotopy type of that stratum, regarded as an infinity groupoid. So importantly, this functor here is conservative. Its fibers are Kahn complexes or infinity groupoids. That's another important feature of this. What else is true? Well, so by the way, I'm missing hypotheses here. The hypotheses are that X is a sufficiently nice stratified space and that P is an Ethereum. So sufficiently nice means hereditarily paracompact, and it means that the stratification is conically stratified. So that first thing is probably not all that interesting, but the second thing is a slightly subtle condition that you have to try and get at geometrically. But I'm going to leave that. It includes all Whitney stratified spaces. What was I talking about? Oh, right. So there's this map here. I should tell you something about this map. It's that it's a weak homotopy equivalence. Is a WHE, weak homotopy equivalence. That's telling you that if you take this infinity 1 category and you invert all the non-invertible 1 morphisms, you're going to get an infinity groupoid, and this is going to be the infinity groupoid you get. And now, last but not least, I don't know why my voice is breaking, but last but not least, we have that if I look at the P constructible sheaves, so I'm going to look at the category of sheaves on X that are P constructible, in the sense that the restriction to the strata is locally constant, then these are the same things as the functors from this thing that I've built into, well, in this case, pi finite spaces. because I've demanded that the values of my locally constant sheaves be pi finite. I beg your pardon?
Are you missing an over P?
Yes, thank you. Good. Okay, so this is the basic idea, is that when you pass to stratified spaces, spaces are the same things as infinity groupoids, and stratified spaces are the same things, sort of, as infinity categories, but not all infinity categories show up. In fact, only these precise ones show up. For example, if I look at the monoid of natural numbers as a one-object category, that can't show up by this process. Right? You can't get that. But that's okay, you can still get a lot of stuff. In fact, here's now a theorem of, well, several people. So, John Wolfe and his student Nand Lal Sylvain Duteau, and my student Peter Haine all thought about the same thing at the same time and came up with the following, which is that if you look at this functor, which is like the singular simplicial set, but it's the relative singular simplicial set, and you think of it going from stratified spaces. These are stratified topological spaces. Maybe I'll emphasize that. And now I have to resort to the kind of chalk I don't want to use. Well, I've avoided it for long enough. It's awful. To now, so what can I go to? I can go to quasi-categories with a conservative functor to P. This is an equivalence of homotopy theories. I was very careful to say not that it's equivalent equivalence, because we actually don't know yet that there's really a model structure on this side. At the moment, all that seems to be known is that there's a semi-model structure, which is kind of annoying, but that's life. There's a perfectly good model structure here that gives you this. But anyway, it's an equivalence of homotopy theories, and that's good enough for me.
But the weak equivalences, the map that are mapped to weak equivalences over there?
Yeah, the things that are weak equivalences here are the things that are stratum-wise weak equivalences and link-wise weak equivalences. So this is the class that was identified by Miller. So I choose to use this as an excuse to work on this side of the homotopy theory, because what I'm trying to do is I'm trying to port this picture into algebraic geometry. And so I'm interested in working with these guys. And so from now on in this talk, when I say P stratified space, I'll actually be thinking of an infinity category with a conservative functor to P. Good. So now, this is telling you about this sort of story for stratified topological spaces. I'm going to skip this part of the story, but I'm going to go straight to this exodromy story for infinity topoi and for schemes, just for the sake of expeditiousness. So the idea now is that, well, let's see, maybe I'll leave this on the board for a second. The idea now is that we want to be able to capture the kind of information that is contained in the category of constructible sheaves on your favorite scheme. So I'm interested in this statement. So I have constructible sheaves. Remember, what does this mean? This means that it's constructible relative to some finite constructible stratification of the Zariski topological space of X. And then this should be equivalent to, well, functors from some new gadget, which I still haven't quite defined yet, into pi finite spaces. That's what I want. So I need to say something about this in order for you to see why this is true. First thing I need to say is about this business of being able to choose your stratification. So for that, let me make the following observation, which, well, this is an old observation. Maybe just a theorem. Sorry. An old theorem of Melvin-Hochster. The following are equivalent for a topological space S. 1. S is equivalent to, or homeomorphic to, the limit of the profinite, or sorry, the finite constructible stratifications. Right, so I have all the various finite constructible stratifications of this topological space, and I'm just going to say that that's the limit in the category of topological spaces. Equivalent to that is that there exists a scheme.
Sorry, I don't understand that condition. How is a stratification a space?
I mean, it's the poset is a space with the Alexandrov topology, and I'm just taking the limit over all those things in the category of topological spaces.
Poset underlying the stratification is what you take.
Yeah. And equivalently, there exists a scheme Y, quasi-compact and quasi-separated, such that S is homeomorphic to the Zariski topology on Y. So the statement is that the topology of any reasonable scheme is actually completely controlled by finite posets. Right? It's a pro-object in finite posets. In other words, the topology of schemes is the same thing as the topology of pro-finite posets. There's no difference. These are often called spectral topological spaces. And this is some motivation for the definition of constructible sheaves for this topology in algebraic geometry. Because after all, what am I saying here? I'm saying that you're going to form the colimit over all possible finite constructible stratifications of the P constructible sheaves on the étale topos of X. And so this is some sort of motivation for this definition on this side. But it also helps us because it also says that, well, if I can tell you how to do this representability for a fixed finite constructible stratification, then I can pass to colimits and I'll have my general statement. Good, so let's do that. So here's the theorem. And this is from this paper, whose archive reference is over there. If X is quasi-compact and quasi-separated again, then for any finite constructible stratification X to P, there exists a pro-finite infinity category along with the conservative functor down to P, such that what you want is true, that if I look at the P constructible étale sheaves on X, then that's the same thing as functors from this guy into pi finite spaces. And this is what I call the exodromy equivalence.
Pro-finite?
This is pro-finite.
What does pro-finite mean?
I mean that it's a pro-object in the category of finite infinity categories.
Actually, like finite.
Yeah, I mean, so if I think of these things as stratified spaces, right? I can talk about finite stratified spaces. Right? It just means that all the Homs are finite and over a finite poset, and then I'm taking pro-objects in that category. This is exactly what I'm getting. If you like, this is a pro-representability statement. And now I can pass to limits and get this for any spectral topological space, S. So in particular, I can get it for the spectral topological space underlying X itself, the Zariski topology, and that gives me exactly what I want. And now I won't even bother to put the slash over anything because I'm implicitly putting the slash over everything. But I'll put étale here to remind you that that's what I'm talking about. Maybe I should do it here too.
So now, what is the left-hand side? What, as a what?
Oh, sorry, this is C and STR.
Okay.
Is that what you were worried about?
Yeah.
Good. There is a statement of the kind that you want. I probably won't have time to come to that, but I can tell you about it. You can, I mean, yeah. Well, let me leave that for now. All right, so what is this thing? And how do we understand it? Well, so the first thing to observe is that when P is the one-point poset, you already know what it is. I wrote it down before. It's just the usual étale homotopy type of your scheme. But this is some fancier stratified homotopy type, so I better at least give you a non-trivial example. And so first, let's write down what you get in the case of, say, a DVR. That's the next simplest thing I can think of after spec of a field. So let's see. So let's say that A is a DVR. And then the underlying topology is the Sierpinski space, right? It's brackets 1 with this Alexandrov topology. Right? There's a closed point and an open point, and nothing else is going on. So closed point S, open point eta. And now I'm supposed to give you a category, right? And that category is supposed to have a conservative functor down to brackets 1. And well, this category has two objects up to isomorphism. And it has a groupoid here, some maps here, and a groupoid here. So I can give you the entire structure of this category by giving you three pieces of information. I can give you this groupoid when I cover this up. I can give you this groupoid when I cover this up. And I can give you the space of maps, the space of sections over brackets 1. Right? I can look at the space of sections, and that's a third piece of information I have to give you. If I give you those three pieces of information, then I've told you everything. All right, so what are these three pieces of information? Well, here's the closed point, little s. Here's the open point, eta. And over the closed point, what do I have to be getting? I have to be getting the absolute Galois group of that closed point as a space. Over the open point, well, I have to be getting the absolute Galois group of that open point, of the residue field of that open point. Nothing else to be done there, right? I have no control. The interesting part is in the information here. What are these maps? I always pause here to see if anyone wants to give a guess as to what the maps are. What are the space of sections here? That's right, it's the B of the decomposition group. Now, the decomposition group is only defined up to conjugacy inside here normally, but this map is uniquely defined. Similarly here, this is representing the Galois group of the residue field as the quotient of this by the inertial group. And this is perfectly correct. This is actually a canonical diagram once you pass to classifying spaces. The good news is that this happens all the time. This is the story for the curve, or for a DVR, but it's true for any curve. If I take a curve over a field, then this exact same description tells you everything. The objects are the points, including the generic point. And for each one of those, I have a copy of one of these. And then the poset's kind of boring, right? The poset, if I take a curve, the poset is only height 1. I have the generic point, and everything is a specialization of the generic point. So there's nothing really going on. And so in between each of these, I have the decomposition group of the local ring. And that's the whole picture. How am I doing? For surfaces, this gets a lot more complicated very, very rapidly. This becomes a much more complicated and rich story. I actually can't even give you really good computations except for sort of trivial stratifications. I can't do something very general for you yet because the posets get involved. Even with surfaces, I'm struggling to say something intelligent about that.
So you get a complicated poset, but the terms should be describable.
The terms are describable, that's right, that's right. So for every pair of those things, then again, so in fact, I mean in general, let me say the following. Actually, I'll leave this where it is. In general, let me say the following. I can give you a description of the category. Let me do that. Because one of the wonderful things that happens is that you're taking this limit over these posets, and each time you have something that seems quite complicated, which is a profinite infinity category, and you're taking a limit over these constructible stratifications. And in the limit, you end up with a 1 category. And that 1 category comes with a topology to remind you that it was a profinite thing that you just did. But apart from that, that's the object. So it's quite a down-to-earth thing. So let me tell you what that down-to-earth thing is. So I should send out a signal now that I'm probably not going to be able to say anything about endodromy. I apologize. But if you have questions, I'm more than happy to answer. In fact, ecstatic is the right word to answer. So let me tell you what... What's that?
Sorry.
Did you say no one would be ecstatic to listen? Is that what you
to see you being ecstatic, though, up there.
All right, so I'm going to just tell you about a category here. This is going to be just a 1 category that I'm just going to call gal x, just to be sly. So the objects, this is just a 1 category. So the objects of gal x are geometric points. By which I mean, if I look at this, then omega has to be a separable closure of the residue field of the image. Okay, that's what I mean by geometric point. I don't mean any old algebraically closed field or any old separably closed field here. I mean specifically one that is a separable closure of the residue field of its image. So that's what the objects are. And the morphisms, what are they? Well, suppose that I have 2 of these. So let me tell you what the maps are from, say, x to y. Well, so what do I have to do? I have to try and give you a way I have to give you what a map is from x to y. And so what is it going to be? Well, I want it to be a specialization that goes like this. So I want x to be a specialization of y. So what is it? It's the squiggly arrow that the cool kids do for specialization. So what does that mean? That means that, well, when I look at spec omega mapping into x, I can look at the strict localization. Right? So this is the strict Henselianization of the local ring. And I need to have a section. So this is omega for y. And I need to have a section. This map here is the data of a map from x to y. This is it right there. That's what it is. That's all it is. These things compose. If you're a specialization of a specialization, then you're a specialization. And so this forms a category. That category is this category. That's the category that we're talking about. This infinity 1 category that you get by performing this long construction. I'm rapidly running out of time. But now, so what do we know? So let's just recount what we know. We know that this represents constructible sheaves. We know that this is an infinity 1 category. If we invert everything in the pro sense, we end up with the étale homotopy type of our original x. So this is some sort of weird delocalization of the étale homotopy type of x. And we also know one more thing. Let me say what the one more thing is. And this is the main theorem of that paper. So here's the theorem. So let's let K be a finitely generated field of characteristic 0. finitely generated over Q. And let's consider this functor. And I'm going to want to look at normal reduced schemes of finite type over K. And from this, I'm going to extract, well, some profinite infinity category equipped with an action of the Galois group. So I'm just going to write profinite up here out of laziness. Equipped with an action of the Galois group. The theorem is that this is fully faithful. In other words, this gal x here is actually a complete invariant for, say, smooth varieties over a finitely generated field of characteristic 0. Okay.
Did you say it's always in one category or not?
Gal is always a 1 category.
Why do you write infinity category?
Oh, I don't know. Laziness, I guess. Yeah. It's funny because that's not really lazy at all, is it? Yeah, you're right. Thank you. So these are profinite 1 categories with an action of this BG. I can tell you more or less explicitly what these things are, up to the fact that I don't know what things like the absolute Galois group of Q is. So I don't really have much time to say how you prove something like this, but let me say the following. The way you prove this is really using some higher topos theory ideas. I really don't know another way apart from proving about getting in there and using some higher topos theory ideas. I mean, we really study the étale topos very carefully of a scheme. And in particular, we think of these things as stratified étale topoi, and they're sort of canonically stratified by the Zariski topological space. And then it turns out that those are actually a very special class of topoi that we call spectral infinity topoi, which are the analogs of the spectral topological spaces that appear in Hochster's theorem. So I'm sorry I don't have time to say more, but I'm always happy to talk about this. Thank you.
Questions for Clark?
I'm confused as to the statement of the theorem. If you've got this pi infinity 1 hat for curves, so this is recovering the étale homotopy type.
It certainly does.
It means no more than the Galois group and the pi 1 étale for a curve. And your statement that this is fully faithful, it looks like it implies that if you have isomorphic fundamental groups for curves, then you'd be. So, well, where did that go wrong?
So where that went wrong is that you did something. So she asks, well, okay, so if I take this profinite infinity or profinite category and invert everything, that gives me the étale homotopy type, right? And that's an étale homotopy type with an action of BG. So, like, are you trying to say that that functor is fully faithful? And definitely not, right? Because we know that's not true. But that's because this functor here, the second step, is very destructive. So if I'm taking my category and I'm inverting everything, right? Here I'm actually remembering, and this category remembers the category structure. It knows that, you know, a map has not been inverted yet. But you're saying, but the things like the section conjecture and, you know, all the Anabelian things are about what happens after you apply this functor down here to spaces, maybe I need to say profinite spaces, over BGK. This is a very destructive functor. This is the invert everything functor. Yeah?
My next question, which is, so what sort of geometry goes into proving that kind of statement? As in, you know, what things about K being finitely generated, characteristic 0 with...
Yeah, so the whole point of this story is, when can you reconstruct a scheme from its étale topos, étale infinity topos? That is to say, when can you take a scheme and reconstruct it from its étale infinity topos? And so there are certain things that you see straight away that aren't going to work. So if you have, for example, you know, an algebraically closed field, well, you're stuck, right? Any two algebraically closed fields have the same étale topos, so you can't reconstruct those from their étale topoi. if you have, so the reduced condition, for example, that's because the étale topos is invariant under topological equivalences under universal homeomorphism. So if I take the reduction of a scheme sitting inside that scheme, that's going to be an equivalence on étale topoi. Similarly, the normal condition, I think you could probably get away with semi-normal in this argument. But the normal condition, what is that trying to do? That's trying to keep you from having things like cusps, right? And the normalization there is an equivalence of étale topoi. Yeah?
There's that article that I know you know of by Blavatsky.
Yes, that's what I'm using here. I'm using that theorem in the course of doing this.
Okay, so the theorem of Blavatsky that the étale topos recovers.
Yeah, thank you for saying that. Yeah, so this is I should have written his name here. Voevodsky wrote an article in 1990, 1989. It's one of his juvenilia. Let's go with 89, I'm not quite sure. In which he shows that you can recover a reduced normal scheme over K from its étale topos. And that's the key thing that we need in order to be able to do this. And that's where these conditions come in, is exactly in that point. So there's this old conjecture of Grothendieck in a letter to Faltings that says that if you take finite type, or essentially a finite type schemes over spec Z, so I'm including things that are finite type over Q, take essentially a finite type schemes over spec Z, and you invert the universal homeomorphisms, and the functor from there into topoi over the étale topos of Z is fully faithful. That's the conjecture. Voevodsky proved that in characteristic 0 along with this normality assumption, which I think you can work your way around. But in general, I think it's wide open. So if anyone here would like to prove that. Yes?
So the question, the point about why you get a one category instead of an infinity category, is that essentially because it's built in pieces out of BGs, and then you have the stratification giving you extra maps connected? That gives you the one category. Yeah,
that's exactly right. It's a one category because you just have B of the various Galois groups, right? And then maybe some decomposition groups connecting the two things. But those are one types as well. So there's nothing higher there. In fact, in general, there's probably an even stronger sentence, which I haven't yet proved, but I hope is still true, that you can actually get this full faithfulness after a finite but sufficient stratification. Because, there are all these statements that are supposed to say that you can recover your scheme after you've sort of chopped it up into pieces that look like these strongly hyperbolic Artin neighborhoods. And that's the kind of thing, I think that stratifying enough to get those should I think that's true. I don't have a proof. I just hope it.
What's the obstruction to the model structure on p-stratified spaces?
What's the obstruction? It's the, well, so there's both a left and a right semi-model structure that don't agree, so it's not a model structure. But it's as always, it's with this lifting condition. You can only get, it's one of these things where you can only get the lifting condition when this guy is cofibrant or this guy is fibrant. That kind of thing. That's the only situation which you can get those lifting conditions, given current technology. I'm sure, I haven't tried to find out what else you could do. That's not my area of expertise.
Is there some way to identify the essential image of that functor?
Yeah, that's an interesting question. I can tell you a whole boatload of things that aren't in the essential image. No, but I no is the short answer to that question. I suspect that if you maybe I better not say anything. I suspect I have a statement for an intermediate thing as a category of infinity topoi, and I bet I can tell you what the essential image is there. But topoi over spec K, but not really. No, not meaningfully.
Let's save further questions for later and thank Clark again. Oh, poster folks, see Dan. Yeah, let's thank Clark.